Okay, so just so you know, and I think I mentioned this yesterday, that 5.5a, where is it? I didn't do a proper job of printing this thing out, so everything's like all in one row. 5.5a is buffer videos. So you can go watch Ms. Spence do buffers, or you can go watch Mr. Colger do buffers. His are nice and short, 5 minutes, 7 minutes, 13 minutes, okay? Similarly, we are coming up on doing titrations, and really, we've actually done titrations already. We're just putting it in the context of titrations. Similarly, for titrations, there's 2 pages of videos here. Whoa. So my videos are like 23 minutes, 13 minutes, 22 minutes, 20 minutes, 30 minutes, 20 minutes, 40 minutes, 10 minutes. But if you go to Mr. Colger, 6, 8, 9, 11, 8, right? So those are quite nice. Yes? So if you're ever feeling like, I don't know enough about determining the percent composition, you can go and say, oh, look, here's a video on determining the percentage composition. Is good? So you know that all of those are there. We are going to start on page 91 today. We are finishing up acids and bases. And actually, just before we get started on that, page 91. I would also like you, we are going to be getting unit 6 piecemeal. Do you know what that means? No. One little thing at a time. So what you're going to do is you're going to get a duotang. You have one of the colors back there. It will be one of your colors, and I'm not buying a new set. And you're going to come up here. How many pieces of paper are you going to take? You're going to take 1, 2. You should see a picture of a lion when you're done, okay? And then you're going to take this and put it in the duotang. I will be making more pages and a cover page, but not today, because I just threw this together so that you can do this really easy part of Unit 6 this weekend, okay? It's about 20 minutes worth of work. It's just watching Tyler DeWitt teach you some really easy stuff, okay? So come get 2 pages and a duotang.
Okay, you go to the pages, I'll go to the duotang. Oh, I know. Yo, you guys want black, gray, or orange? Your favorite is everywhere. Oh shit. Also trading your fingers. Yo. Buddy, I'm scared. No, we're so much. I just don't get on. Oh. You still want orange? You have a gray one? I mean, you still have a gray one. Yo, Daniel, may I have a gray one? I know that's here.
If anyone wants a sticker for the front of their book to label it, there are stickers. Help yourself.
Oh shit. Oh, sorry.
You're talking about these in bio.
Yep. 2 pages. 1, 2, and then you should see a lion underneath those pages. Huh?
Leo says
Leo the lion says grr. They're just for labeling the front if you want.
No, I guess we just like that. The one being cost, using Asian.
Did we do this already?
No, we talked about this in bio.
Okay, I was like, hang on, I do not remember doing this. Wow. Well, our book, technically the book for this course is called Chemistry, the Central Science. Because it is central to everything, right? Okay.
Let's be real, probably. Yeah.
So, we're on page 91. And up till this point, some of you who were doing the assessment on that one day when we had long blocks didn't get to do our most recent titration. If you're feeling titrationless and you would like to do a titration at some point, let me know, okay? But we can also do a titration in a slightly different way. What we've done up till this point is we have added an indicator and we've just run it until the indicator changes color, yes?
Yeah.
But the other way to do a titration, an acid-base titration, is to stick a pH meter into the thing at the bottom. Why is it not writing? Please write. There we go. Stick a pH meter in there and measure the pH as time goes on. Here is a go figure question. Where's go figure? In which direction do you expect the pH to change? In which direction do you expect the pH to change as NaOH is added to the HCl solution? Yes? How does a pH meter work? It would interact with hydrogen ions, I would assume. I don't know the real ins and outs of it. That's something you would want to Google probably. Yes? Pardon me? What does everybody think? Is the pH going to stay the same, go up, or go down? Up. Why? We're adding base, okay? So the pH will increase. Yes. What's that? No, that's okay. Yes. 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 But it can't shift right because we're talking about adding it to HCl, which is a strong acid. So it's already all dissociated. So what's happening is when you're adding the NaOH, you're simply taking H ions out of solution. Yeah? So far, so good? We are going to come across that question later because we will be dealing with weak acids later. Okay, and we'll hit it then. Okay? But for now, when NaOH is added to HCl, the pH is going to increase. So here are some words that you may recall. Do you remember the word titrant? What is the titrant? The thing in the thing, yeah. It's the thing in the, what do we call that long tube? The burette, which can also be spelled burette. Okay, either of those are acceptable. Okay, and this is our titrant. Normally, the titrant is the thing that you know the concentration, okay? So this is known concentration. Huh? We're good? Now, what do we call the thing that's in the flask? Yes, sorry.
Okay, this might definitely be right.
That's okay.
So in order to build the concentration substance, we need to first understand the concentration of the cell.
Yes.
So what was that first thing?
Okay.
Down, how do we initially find the concentration?
Oh, right, it's just turtles all the way down. I don't know if you've heard that expression, but anyway. No, there actually is a way, because what you'll do is you'll make what they call a primary standard. Do you remember what a standard is?
Yeah.
See if you can remember what a standard is. In the context of solutions, a standard solution. A solution of known concentration. Now, a primary standard just a second. A primary standard is a standard where you know the moles because you measured the mass. Okay? It has to be very pure, which is the problem with many other things, which is why we end up standardizing by comparing it with something else, because a lot of substances, NaOH, for example, is never really pure because it absorbs water from the atmosphere. You actually get these little pellets of NaOH, and they often look shiny and gooey, and they are sticky, and that's because they have absorbed water from the atmosphere, so that's not pure NaOH anymore. Yes? Can you use distilled water, Anne? As a titrant? What would it be reacting with?
You would just add water to all the
But what are you finding the concentration of by adding water? Okay. Well, the thing is, water's the solvent, so it's not really. No. The answer is no. Okay? Yeah. So a primary standard is a standard where you know the moles because you measured the mass. In order to be a primary standard, the substance must be very pure, and here's a fun word for you: non-hygroscopic. Now, hygroscopic. Okay. It's almost like hydroscopic. I'll put a little dash there so it doesn't look quite so weird. Non-hygroscopic. It still looks really weird. Mercury, I think, has a hygro in it. Hydrogyron or something like that. That's why it's Hg, because it's liquid. Yes? So I think, I could be wrong. Huh? What? About the mercury? What did I say about mercury? I said I thought its name came like from something like hydrogyron. And that's why it has the Hg. Yeah? I think. But I could be wrong. But Hygro is almost like hydro, like hydrate. Yes. So hygro has to do with water. And if you are non-hygroscopic, you do not absorb water from the atmosphere. So the substance, in order to be a primary standard, are we okay with this little notation for primary? A 1 with a little degree sign? Okay. If you're not in biology, you might not have seen it before, but that's primary. Okay? 1 with a little 0, primary. I'm pretty sure I have this written down in like tidy form somewhere in this document, but I'm not sure where. So, let's just do it now, okay? To be a primary standard, the substance must be very pure and non-hygroscopic. That way, when you weigh its mass, you know that that's the only substance you're getting. You're not getting all sorts of other weird stuff, okay? And you will make the solution in a very precise volume. Yes?
How do I prove that something is non-hygroscopic?
You know its properties because people have researched its properties, right? And you choose from, like, what is it, potassium phthalate or something like that is one of them. Oxalic acid is a good one, okay? Oxalic acid comes as a hydrate, but it is a hydrate with a dot H2O, so it has a specific ratio of waters on it, and it won't absorb any more. Okay, so it's not just randomly absorbing water, it has a definite, it's like oxalic acid dihydrate, H2, C2O4 dot 2 H2O. That is a good primary standard. Because beyond those waters, which we know about, and we know exactly how many there are per thing, there's no excess water no random quantities of water being absorbed onto it. Yes? What here do you actually need to know? You need to know the term primary standard, okay? You do not need to know what a good primary standard is. You don't need to be able to pull one out of the air, okay? You should know that it is pure and non-hygroscopic, and you should know why that's important. It's so you can measure an exact mass. And you should know the term standard, meaning of known concentration. And did I say primary standard? Yeah. So that's what you need to know. All the other stuff is just kind of gravy. Okay? Yes?
It needs to be pure and non-hygroscopic. So I'm good. But what about the figure of a substance? How is I, even being with I, supposed to know it's pure?
You don't. You just know that you order things from a chemical company.
How do they know?
How they do testing on it.
How do they do that?
Well, they'd probably react it with something else, and then it's turtles all the way down. So you know what I mean, right? Yeah. But I mean, over the years, people will have done various tests on various substances, reacting this with that, and that with that, and and then you come up with this body of knowledge about this chemistry, about this particular chemical. This particular chemical does not absorb water from the atmosphere. That's something you'd be able to figure out, right? For one thing, you could just, do a drying on, you could dry it, put it in an oven, dry it, and then just let it sit there, weigh its mass before and after, and you'd see if it absorbed water. You know what I mean? So that would be one way of knowing that it's non-hygroscopic, is just like, does it change mass if it sits there for a while? right?
I agree.
Yeah. Okay, please define for your partner the equivalence point.
Oh.
It's the point where what are equal? Products and reactants? That would be your half equivalence point. The equivalence point occurs when the reaction is complete. And I'm going to say perfectly complete because there's no excess of either reactant. Sometimes people like to say that the equivalence point is when the moles of acid equal the moles of base, but then you run into problems if you have a diprotic acid, because you'll be at the equivalence point when the moles of acid equal half the moles of the base, because you've got a 2-to-1 ratio, right? So I like to avoid saying when the moles of acid equal the moles of base, because what if you have HCl and strontium hydroxide? You'll require twice as much acid as base to get to the equivalence point. So it's when it's, let's see if I've written it down here. Oh, look, moles of acid equals moles of base. Ah. I'm not that happy about that. It's when, a better way to say it is it's when the amount of titrant added is just enough to completely neutralize the analyte. I actually like the way I said it over there. It occurs when the reaction is perfectly complete. You could say when the stoichiometry of the reaction is perfectly fulfilled. Do we like that way of saying it? And in fact, the equivalence point is also known as the stoichiometric point, which takes into account this business of the stoichiometry being perfectly fulfilled. The stoichiometry, that is the mole ratio. So if the reaction is a 2-to-1 reaction, it means, what do we have at the equivalence point? We have exactly 2-to-1. Okay, if it was a 3-to-2, I don't know where you would have that, but if it was 3-to-2, you would have exactly 3-to-2. Okay, whatever the numbers are, the coefficients are, that would be your ratio of reactant to reactant. Okay, So the equivalence point is actually also known as the stoichiometric point. Do you remember what an analyte is? The analyte solution. Tell your partner, what is the analyte solution? It's the thing that you analyze. Yes. Let me know if I move the screen around too much, if you need it to stay more steady. And if we're analyzing it, do we know its concentration?
No.
No, it has an unknown concentration. An indicator is a weak acid or base. I don't like this language either. I'm going to be fixing this. Is a weak acid. That's supposed to be a slash. I don't know why it goes all crazy when I do slashes. It's a weak acid slash base that is added to the analyte solution. And if you choose the indicator correctly, which you might or might not do, depending on how clever you are, it will change color at the equivalence point. If you choose wrong, it will change color somewhere other than the equivalence point. So one of the things we'll be doing is looking at selecting a good indicator. Okay? Yes? It is if you have a strong acid and a strong base. But what if you have a strong acid reacting with a weak base? Turn into, so the weak base would, like, let's say we have NH3. What would NH3 turn into if it reacted with HCl? NH4. And then you have, at the equivalence point, all you have left is products, NH4. What is NH4? It's a weak acid, so your solution will be slightly acidic. Yeah? Do you remember when we were doing those calculations the other day? And we were like, oh, we're adding a strong acid to a weak base, or we were adding a strong base to a weak acid and saying, what did we get at the equivalence point? That's what we're going to be looking at today as well. Okay? So we're putting it in the context of a titration. All right. The point at which the indicator changes color. The point at which the indicator changes color is called the end point. I love these because they're both E points. We have the equivalence point and we have the end point. They are not the same. If you do a good job selecting your indicator, the end point should line up with the equivalence point. The pH at which it changes color should occur at the equivalence point. Okay? So the end point the end point is where the indicator changes color. So the equivalence point is where the stoichiometry is perfectly fulfilled. The end point is where the indicator changes color. What is a titration curve? This is where we take data, we put the pH meter into the solution, and we take readings all the way along as we read it. You can actually attach many of these probes to like your phone or a computer, and it will plot in real time as you go, so you can actually see the change in pH. back in the olden days when I did this, you would put the pH meter in and then you would add like 1 milliliter and then you would record the pH. And then you would add another milliliter and then you would record the pH. And then you would add another milliliter and record the pH. And then you would plot them on a graph. And then when it started to go, it would go like up, 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 up slowly. All of a sudden it would start to go like this. And you would stop measuring in 1 millimeter increments and you'd be like 0.5 or 0.2 milliliter increments. You'd do little point until you got here and then you could do 1 milliliter again. It was really tedious. Yes? Why does it go like that? Well, that's what we're going to talk about. That's what we're doing today. Okay? So here we have a titration curve. And it is the plot of the pH of the analyte solution versus the volume of the titrant added. Whoa. And I need to fix this, because that's just an arrow from a screenshot that's hanging out there. All right. Now, what do we know about the pH scale? pH scale is logarithmic. So if this is pH, let's just say that this is pH equal to 1. That means that our hydrogen ion concentration is 10 to the -1, right? And if we are at the equivalence point, this right here, this point right here, would be the equivalence point. That's a terrible arrow. It's not even pointing the right place. If this is a strong acid plus, or sorry, a strong acid plus strong base, yeah, that's what I wanted to say. Strong acid plus strong base. What would the pH at the equivalence point be? It would be 7 because when we neutralize, let's say, for example, we had NaOH plus HCl. Who are the products of that reaction? NaCl plus H2O. And at the equivalence point, how much reactant do we have left?
0.
At the equivalence point, how much of the reactants is left? None. Okay? So we have no strong acid, we have no strong base. At the equivalence point, all we have is salt and water. Now, what's the pH of water, for starters? 7. Okay, so water is pH equal to 7. Now, how do we tell the pH of a salt? Chat with your partner about that. How do we know the pH of a salt? If you're trying to find the pH of a salt, what process are you considering? Hydrolysis. Okay, so you're going to look at those ions, and what are you going to say?
Do they hydrolyze?
Do they hydrolyze? Yes. Okay, so you look at the ions. Do the ions hydrolyze? And here we have NaCl. Do those ions hydrolyze? You should be able to tell your neighbor just like that if those ones hydrolyze. Those are some of the easiest ions. Does sodium hydrolyze? No. Does chloride hydrolyze? No, because it is the conjugate base of a strong acid. So Na plus Cl minus, no hydrolysis. No hydrolysis. So if our salt does not hydrolyze, what is the pH? 7. Okay? It's not 0, it's 7. Okay? So if the salt does not hydrolyze, the pH is 7. So we can label that on our diagram. 7. Okay, we got pH 7. You actually know how to do that already.
Yeah, but I forgot.
Okay, so what you're going to do is you're going to draw a Ricfa table, which will show you that everything ends up as the product. So you'll find the moles of the product, and then you will divide by the total volume, and then you will do a rice table and a K whatever.
Great.
Yes?
Yeah.
Yes. Okay. So down here, we have excess acid. So the pH is below 7. And above the equivalence point, we have excess base, which means that the pH is greater than 7. Okay, and at the equivalence point, we have NaCl and H2O only, therefore our pH is 7 at the equivalence point. Yes? I'm sorry, what? Yes. The equivalence point is always in the middle of the steepest part of the curve. Okay? Where's a good place to write that? Over here. Okie dokie. So its equivalence point is always in the middle of the steepest part of the curve. Now, titration curves are one of those things where you just need to spend a little time soaking in them. So we're just going to, go through, and then you're going to do some practice, and then you're going to go through, and then you're going to do some practice. And you know what I mean? Like they can be a little confusing when you first start them, but then they become easier and easier. I actually found a great resource this year that has particulate diagrams for titration curves, and we can run it a little bit like a Poggle, and maybe we'll do that on Monday. Okay. So, suppose that our analyte is hydrochloric acid, blah, 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 blah. Oh yeah, this is fine. And the titrant is sodium hydroxide. Oh yeah, this is just saying this is the curve you'll get. And in fact, this is a better diagram than the one on the previous page. The previous page just gave you the overall shape. Strong acid, strong base. You'll notice that this area is fairly flat. This area here, from here to here, is long and very steep. And this area at the top is fairly flat. So what I'd like to ask you is, what species is responsible for the pH here in the yellow zone? So you'll notice how the points are numbered. Here we have 0.1. Here we have 0.2. What species is responsible for the pH there? The acid, which acid in this case? HCl. Okay. What species are responsible for the pH at the equivalence point? Have a chat about that. What are the only species present at the equivalence point? NaCl and water. Because remember, all of the NaOH has reacted, all of the HCl has reacted. Okay, all of the HCl and the NaOH have reacted and are gone. Okay. And what is responsible for the pH from 0.4 onward? NaOH. So basically we have HCl, then we have water and salt, and then we have NaOH. Yes?
So that the equivalent volume of the lead factor would be determined by product.
Yes. The equivalence point of the titration of a weak acid or a weak base would be determined by the hydrolysis of whatever that salt is that is produced. It's determined by the products of the reaction. Okay. So at 0.1, it's all H3O plus. As we add NaOH dropwise, the H3O plus starts getting consumed. But the analyte is still acidic due to the unreacted H3O plus. At 0.2, this is the pH recorded at a time point just before complete neutralization takes place. And 0.3 is the equivalence point. That's where all the acid and all the base are all gone, and this is all we have. Salt and water. And then after, at 0.4 NaOH, as the addition of NaOH continues, the pH starts becoming basic. And so we have mostly base. Is good? Okay. Here is a fun question for you. Fun. What is the initial concentration of the HCl solution according to that graph? Shh, don't answer it out loud. Let people answer it themselves. What is the initial concentration of the HCl solution? I want everyone to write down their answer in the box. Maybe write it in pencil, so if you aren't sure, you can change it later if you need to. It's all good. Yeah.
I would know. You have,
Did you get 1 times 10 to the negative 2 molar? Because it is a strong acid, it dissociates completely. So whatever the concentration of the H plus is, will be the concentration of the HCl. Okay. Here we go. Oh, look, a go figure question. I am literally just stealing things out of that big black book, right? What volume of NaOH would be needed to reach the equivalence point if the concentration of the added base were 2.0 molar? So you can put your response right in this little box here. Try that question, please. Oh, and there's some information at the bottom. Where did it go? Come back. Don't forget, down at the bottom of the page, it tells you the concentration of the NaOH. Okay? See if you can solve that. Right? This graph that you're seeing here, this graph is for, it tells you in the little description, the graph is for 0.100 molar base, and you're being asked what the concentration of, what volume of NaOH would you need to reach the equivalence point if we changed the concentration of the base to 0.2 molar. Okay, so that's what we're looking at there. Yes. What? Okay, so the graph, the picture shows the titration of a strong acid with a strong base. Shush! The pH curve for the titration of 50 milliliters of 0.1 molar solution of acid reacting with a 0.1 molar solution of NaOH. That's what this picture shows. That is this graph here. So you have some information when the concentration of the base is 0.1 molar. And now we're asking what happens to the volume of NaOH to reach the equivalence point if we change the concentration of the base to 0.2 molar. Yes? So the picture is for 0.1 molar. What happens to the volume of NaOH if we change the concentration to 0.2 molar? Okay? If you really don't know where to start, what I'd like you to look at is I would like you to consider with the 0.1 molar base. And remember, this diagram is with 0.1 molar base. With 0.1 molar base, how many milliliters was required to reach the equivalence point? 50. Yes, we read down here. And we have 50 milliliters. So that's with 0.1 molar. What volume would be required if we changed the concentration of NaOH to 0.2 molar? What have we done to the concentration? We've doubled the concentration. Therefore, what will happen to the volume required to reach the equivalence point? It will be half. Does that make sense? Okay. Okay, volume of NaOH required would be halved. So, in other words, how many milliliters? 25. Time is class over today? 54. How are we doing? We're almost there. Okay. Now, let's take a look at these little pictures underneath. This little point goes here. What do you see in solution there? What do you see in solution at the very beginning? You see H and Cl. That's it, right? Okay. Now, our next point. Can you guys tell me what this point is right here? Do you know what that point is there? That is our half equivalence point. And you'll notice we have H plus one of them has been reacted, right? Because we now have an H plus reacted with an OH minus to make an H2O. I'm just going to put an H2O here to represent the OH coming in with the H. Yes? Does that make sense? Yeah? Okay. So we have half the hydrogen that we did before. And then finally, once the H plus is completely neutralized, instead of having H plus, we have an H2O and we have an H2O just added to our solvent. And we have lots of Cl minus. And we have Na plus, Na plus. So at the equivalence point, what species do we have? Water and salt. Now, after the equivalence point, we have salt. You can see we've got one NaCl, two NaCl, but we also have another Na because we added an NaOH. Yes? Okay. Now I'd like to ask, how much actual calculations have you guys done on those ones where it was like calculating the concentration, like calculating the pH at various points when we added a, what part of the book am I referring to? Let me look in the book and give you a page number. Okay. If we are looking at page 74, how much of page 74 have you done? Yes. What's that, just 1 to 4? Did you guys actually do 1 to 4? Okay, so here's your homework. Page 74, numbers 5 to 7. If you didn't do 1 to 4, do number 1 to 4, if you haven't already done them. Let's also remind ourselves of some strong calculations. Let's do page 63, number 1. Okay, that's a strong calculation. And in addition to that, what else would I like you to do? The whatever you color your new book is, you're going to do the read 5.1a. Watch the video, take the notes. Thank you.